Okay, Tony Mormino, HVAC TV. Welcome to another podcast episode. We really appreciate you joining us. And today I got Kyle Troskot here, and we're going to talk about something that's kind of new to me. I know it's been around a while, and I'm looking forward to getting into this. It's what it's called is liquid desiccant dehumidification. So we're gonna get into this in a minute. It's a different way to dehumidify the air. We have, vapor compression cycle. This is the mechanical cooling. We have chill water with active desiccants, and we have liquid desiccants as well. So Kyle, good morning. How you doing today?
Good. I appreciate the time. Excited to be here.
Great. We're glad to have you here, and look forward to talking about this topic. Again, you'd asked me before the podcast what my experience is with liquid desiccants, and it's very little. We used to have one of our Florida offices when we were in Florida repped, I believe, your product. At least it was an active desiccant product. I'm pretty sure it was yours. So I heard, some people talk about, hey, here's how we applied it. Here's what we've done with it. But let's just go through, I was thinking as I was just, bloviating here, maybe we talk about desiccants in general and then work towards the liquid aspect, which is a new kind of desiccant for a lot of people that are listening here. So we have a lot of engineers, a lot of mechanical contractors. So why don't we start with desiccants 101? What is a desiccant? What does it do? How do we use that in air conditioning?
Sure. So easiest way to recognize the desiccant material is probably equate to those little silica gel packets, right? You find them in shoe boxes, protein powders, etc.
Mm-hmm.
They're materials that like to pull water into them. Driving mechanism, which we could talk about a little later in more detail, is vapor pressure. We'll get into that. But effectively, when you pass air through these desiccant materials that are exposed to water, they have a strong affinity for water and absorb water into them. So active desiccants or solid desiccant materials, typically in HVAC, we see them in a wheel form. Typically, there's a lot of manufacturers that utilize wheel-based active desiccants where, you have a wheel rotating through an airstream. It's going to, not to be confused with energy recovery wheels, though some of them can be coated with desiccant material on them to help their latent removal process. But effectively a wheel that passes through the airstream, traps water in it. You move that wheel or portion of that wheel to another airstream and effectively release that water back out. So that's, I think, what most of the market, at least in terms of HVAC, has been exposed to traditionally with desiccant materials that are quote unquote solids.
Right. So let's recap that for a minute for those listening, because we get a lot of new folks listening too. And it's so funny. It takes I don't know, 25 years to kind of feel like you think you know a lot of stuff in this industry. That's what it's taken for me. So, desiccant material, silica gel, you find those sneakers. So you mentioned something called adsorption, which is different than absorption, I've learned over the years. So an adsorption process doesn't change the material that's taking on the water. It's more like a sieve. It's like a hole that traps the water in it because of the vapor pressure differential. And then you're able to release that water in another lower or higher vapor pressure area, right? So that's the adsorption. And then you talked about energy recovery wheels, which we use all the time in the Southeast, which is great. It does save some energy of the unit, but it really doesn't help to dehumidify the space. That's a big misconception. But it does help with energy savings. So this is not an episode about energy recovery, but just want to clarify that. What we're talking about today is actually dehumidifying the air so that when we provide it to the space, it's got a lower dew point than when it came into the desiccant. And a lot of folks are familiar with active desiccants. We see them all the time, usually on extremely low dew point applications. Okay. We're talking about in the negative tens, teens. I was in a factory that had these and they had a negative 60-degree dew point. So this is a really rare situation. That's where you see the active desiccants, which, adsorbs the water, and then you use a high heat source to drive that water off the wheel. Okay. So that's a little bit about desiccants. Did I miss anything there before we move on?
I think that's pretty good coverage on active or what I would coin as solid desiccants.
Got it. So, it was so brilliant. We don't have to add anything else to it. That's what you're saying. Okay. I like it.
Yeah. We cover the main parts.
That's what you meant
Drawing
to say.
water in and then rejecting water out with a high grade heat source typically.
Got
that
it.
chases
Got it.
very low dew points. Yep.
So desiccants could be solid and they could be liquid. So let's
Yeah.
say this is my way to segue into the liquid desiccant. So you tell us how this liquid desiccant stuff works.
Sure. So just like solid desiccant materials, there's turns out there's liquid desiccant materials out there as well that exhibit similar properties. Kind of a strange concept because it's a liquid that wants to pull more liquid into it is the easiest way to describe it, which for a lot of people, it takes a little bit of wrapping their mind around that a water could want more water.
Yeah,
But
I actually have a chemical engineering degree and I can't even wrap my mind around that. So not that
yeah,
not that I use it at all anymore, but
yeah.
forever. But anyway, sorry to interrupt you, but go ahead.
No. Yeah, I get a lot of, head tilts and people are like, huh? A water that wants more water in it. But yeah, that's the case. So liquid desiccants are typically brines. So we're talking saltwater solutions here.
Mhm.
Most common in the market that I think historically people have been exposed to is lithium bromide. That's actually a technically classified as a liquid desiccant material. Other ones out there, calcium chloride. The one that Mojave uses specifically and is becoming prevalent in liquid desiccant system manufacturers out in the market today is really lithium chloride. So
Mm,
salt solution. Um, the way you could think about it is similar to an active desiccant. You have this salt solution as the air passes through some sort of either membrane-based system or
right.
actively passes through like a wetted media. Effectively, it's going to not adsorb but absorb. So slightly different process.
Okay.
Moisture from the air. So it's an absorption process. Which, to clarify the difference for the listeners here, adsorption is trapping water vapor on a surface and then re-releasing that water vapor from the surface. Absorption, a little different. We're actually absorbing water into the bulk of the upper material. So in this case, this water is physically condensing, or the saltwater brine solution is actually condensing water from the air. So you have phase change. You're going from a vapor, you are
Hmm.
condensing to a liquid. So that volume of the liquid desiccant does get larger. It's diluting effectively. So it's absorbing water from it, and then we can move it somewhere else. And then, similar to an active or solid desiccant material, you can re-evaporate it back out to restart that process.
Got it.
So, yeah,
So I'm learning something new here.
yeah. Uh, there is actually heat associated with that phase change as well.
Right.
So, um, with active desiccants, typically you need post cooling or some form of it gets really hot as it dehumidifies. So you do typically post cooling or something of that fashion.
That's right. Hmm.
With liquid desiccants, there is still heat associated with that process, but it's much less heat than a active desiccant material. So typically the heat rise we see is anywhere from 5 to 15 degrees rather than, as much higher with
Right.
active desiccants where you're leaving in the 80s to, depending on how much you're adsorbing, it could be as high as the 120-degree range.
Sure.
Or
And you
even beyond
typically
that,
need
right?
some sort of post cooling,
Right.
sensible cooling device afterwards, right? Yeah.
Exactly. So effectively, we've harnessed this process to very efficiently manage dehumidification. A couple other things to call out about liquid desiccant specifically. It's not fixed state dehumidification like an active desiccant is.
Hmm.
So with active desiccants or solid desiccants, due to the fact it's just a solid fixed material, it's either
Hmm.
dehumidifying or it's not based off of the airstream that it's in. And you could do some fancy control strategies to try and vary it a little bit, but it's generally on off. You typically bypass the wheel if you're not needing dehumidification,
Hmm.
generally. With liquid desiccants, the amount of dehumidification is actually based on its concentration.
Hmm.
So if you manipulate the concentration, or saying that differently for the viewers, or listeners, pardon me, the amount of salt versus the amount of water
Hmm.
in the base solution before we start dehumidifying dictates its vapor pressure, which is the driving force of how it dehumidifies. So if we vary the ratio of salt to water before it goes into its dehumidification operation, we can
Hmm.
actually vary how much we dehumidify.
So
So
is that
it's
done real time in the
yeah,
equipment?
Yeah, it is.
You have to run
So
out there with a
rather
bucket of brine and recalibrate the
no,
recalibrate the
actually,
salts. Throw some salts in there.
no, it's much simpler than that, believe it or not.
Good.
You just vary the amount of heat going in on the rejection side, which varies how much you're rejecting, and that actually in turn varies how much or the ratio of water to salt on the process side, and that in turn varies how much you're dehumidifying.
Got
So
it.
process side, let's say you start with a pound of salt, a pound of water, or a pound of lithium chloride salt, a pound of water. You think of it like a sponge, right? So sponge is half full,
Hmm.
just intuitively. It's only going to be able to hold half that amount of water. Um, if on the rejection side now, I reject more than that, or more than that original pound. So let's say I reject 1.5 pounds for every pound of salt. Now it's got more capacity to pull water into that sponge. And
Right.
there's some nuance to that control strategy wise within our system, which we don't need to get into in today's podcast. That's a dedicated lunch or something. But
Right.
effectively, it allows you to vary how much you dehumidify without having to just on off, on off. So you get
Okay.
dehumidify more when you need it, you get back off when you don't need it. And the max capacity of how much you're able to dehumidify is really just a function of how much salt and your total volume tank that you have. It's so much
Okay.
greater flexibility in terms of dehumidification.
I didn't know that. That's good to know. So maybe for the viewers, because I actually looked at your YouTube channel. So if you want to see a visual, you know, I don't know what it's called, video graphic of
Sure.
one of these units in action, you can go to their YouTube channel, which is Mojave Energy Systems. I'm looking at it here and check that out. But let's talk about how this works in a pack because I would, unless I see it, I would have trouble understanding. Well, how do you put this in a package unit? Just put a bucket of the
Sure.
stuff in there, or how does it work? So let's walk through a packaged DX rooftop unit, which everybody's familiar with, and we'll do, let's say, a DOAS application. So dedicated outdoor air system, 100,000, let's say, I don't know, 20-ton unit ish conventional unit, which would be, I don't know, 3,000 CFM of outdoor air if I'm doing my math. If I'm doing my
Sure.
math on a podcast
150
live,
to 200
right?
CFM or so.
I think that's about 3,000 CFM. So how does
Yeah.
the air? Well, let's go from the air coming into the unit. What devices does it go through, and how does this happen?
Sure. So process side of the system, very similar to a conventional hot gas reheat style DOAS system in terms of like path. With the key difference, there's no hot gas reheat coil in our systems. So
Hmm.
inlet hood, air comes through a filter bank. You hit a DX coil. Um, Unlike traditional DX systems, with desiccant systems in general, you're typically not chasing a dew point with a coil. You're not trying to. It's the beer can example, right? You're not trying to condense all your water on a coil anymore and then just reheat it back up to temperature, so you're not cold confinement.
Hmm.
So in our systems here, you hit the DX coil, you're going to do your functional cooling with that pre-cooling coil coming off downstream rather than a hot gas reheat coil. We've got this thing called a liquid desiccant absorber,
Hmm.
and basically it's a fixed pad, no moving parts, and effectively we distribute this brine, this liquid desiccant solution through this pad here, and two things happen simultaneously. Going back to the comment earlier about it being an absorption process, it's actually isenthalpic, meaning there's a conservation of energy happening. So it's going to dehumidify and release heat as a byproduct of that phase change,
Right.
condensing water from the air, so going from a vapor to a liquid. So it's dehumidifying and reheating equal parts through this pad effectively. Um, One of the things worth calling out here is as it dehumidifies and reheats, we're able to back to the coil, make sure we're coming off warmer. So we come off warmer, we're chasing enthalpy now with a coil rather than dew point. So chasing a target
Hmm.
enthalpy, and then this isenthalpic dehumidification process dehumidifies you and reheats you at the same time to your target neutral air condition, or if you want cold, you could just overdrive your cooling coil to be cold. And then again, this is where it'd be good to get your psychrometric chart
Yeah, to have a
out.
psych chart. Yeah.
Yeah, yeah. So real good aid if you have a psych chart, but you could think of this like a reverse swap cooler. So rather
Hmm.
than for all the guys that are our psychometric nerds like me, rather than going up and to the left along the psych chart, humidifying and cooling, we're going along that same enthalpy line down and to the right. We're dehumidifying and reheating.
Adding a
True
little heat
conservation
to
of
it.
energy. Right.
Right.
Down to the target, neutral condition or cold condition, and then also the dehumidified condition. And that sheds tonnage and all this fun stuff. Downstream of that, that's really the effective process. So downstream of that, you have a heat section if you want to heat, fan section, and then supply to the building. Now, where things get interesting and a little different is you could think about desiccant and liquid desiccant in general, kind of similar to a refrigerant. It's a medium, right? So refrigerant is what? A medium for moving heat around. Trap heat, move it somewhere else, get the heat out. Now you've got this liquid desiccant, which is also a medium, but it's a medium for water. So we trap water in this liquid desiccant absorber. We pump it somewhere else. So there is some minor energy being consumed in pumping, and we're talking fractional horsepower pumps. We pump it to what we call our regeneration or reactivation side of the system, which if you've dealt with active desiccants, you're probably familiar with those terms. That's the technical term for adding heat to a desiccant to reject the moisture back out of it. So similar deal, we're pumping now rather than a rotating wheel. We're pumping fluid through another pad on a separate airstream, or reactivation airstream, and effectively running this diluted desiccant that's now got all this water trapped in it through it, and effectively evaporating that water out and rejecting that water to ambient. Where things get a little weird or different is we're actually able to do that with a much lower grade heat source than conventional active desiccants. So we talked about earlier, active desiccants need high grade heat sources, 200 degrees, typically plus. So electric heaters or gas fired heaters. With liquid desiccants, we're actually able to do adequate regeneration or rejection of water out of that desiccant fluid with free heat off the compressor. So there is still a hot gas free heat coil that we employ. We moved it to a separate airstream, take outside air in, heat it up with free heat off the compressor system, and then actually use that free heat to reject the water out of that desiccant. So it's near free dehumidification. I say near free because we are using minor pumping energy to move that fluid back and forth, but kind of a clever way to get near free dehumidification. And that's just about 30% of your tonnage.
Wow. So, okay, we'll double click on, we'll double click on that in a minute. Let's go back through the unit, because I think that's helpful, at least for me and hopefully some of the listeners. So let's start at the outdoor air design day. You pick it, 9578. Walk me through the drop through the cooling coil. So there's a conventional DX cooling coil first, the filters and all that stuff. And then there's the liquid desiccant you mentioned on a pad. Is that a cellulose wetted media kind of thing, or
a little bit more exotic?
Okay,
but
gotcha.
Yeah, similar idea. It's a fiberglass.
It looks like a wet filter.
Yeah.
Right, but it's much more robust than that. But that's just the thing that comes to mind. So walk me through the temperatures. What are we looking at? What's for dew point depression and dry bulb? Sure.
So let's do just neutral air DOAS, since you used that topic earlier. So let's say we're targeting a 53 dew point and 70 degrees neutral from the unit to supply the space. In that example here, taking outside air from 9578 comes through the DX coil. You're probably chasing an off coil temperature in the low 60s.
Okay.
Is what I'm going to kind of mentally assume, unless I pull my psych chart out. Because what we're doing is we're trying to chase off coil temperature that matches the enthalpy of the supply air condition. So 70 dry bulb, 53 dew point. I need to come off coil at that same enthalpy, which is probably in the low 60s and saturated, if I had to guess. So let's call it 61 for argument's sake. Now coming off coil, 61 dry bulb, 61 wet bulb, saturated air goes through then our liquid desiccant absorber, and it's going to have two things happen to it. It's going to go from 61 dry bulb, 61 wet bulb, and as a result, 61 dew point. That dew point is going to drop down to 53, and simultaneously, it's going to release 8-9 degrees in this example here of temperature energy, or dry bulb energy, sensible energy. and bring you up from 61 to 70 dry bulb. So again, slanting down into the right for the viewer or listeners, dehumidifying and reheating. It's kind of reverse swamp cooler, de-evaporative heating process, delivering, supply air that's 70 degrees dry bulb and 53 degrees dew point, plus whatever heat you're picking up from the fan, right? So you account for that heat from the fan as well.
Got it. So great. So that the supplier tunnel to me seems very clear. So the reactivation side, am I saying that right? Reactivation side, you're taking the heat that you removed in the DX cooling coil, you're taking that like a normal refrigeration cycle system, the heat we would normally throw out to the atmosphere in the condenser, you're using that heat to reactivate the liquid desiccant. Is that accurate?
Correct. And there's to add a little nuance to it, there is still a traditional condenser on these systems. So three-way modulating valve, the whole gambit, and we're routing hot gas intelligently between our traditional condenser, where you just reject heat to ambient, and this hot gas reheat coil we put in a different airstream.
So there's two coils.
There is two coils.
I got it.
Two condenser coils, right?
Right. Just like you would have in a DOAS package unit, a condenser coil and a hot gas. Okay, I gotcha. I missed that part. Got it.
Yeah, and effectively what we're doing is we're intelligently routing hot gas between these two coils. If I need, going back to my comments about liquid desiccant being variable, if I put more hot gas in the reactivation hot gas reheat coil, I could drive more water out of the desiccant and in turn get more dehumidification. And if it's a part load day, let's say it's 60 degrees and raining, or 100 degrees and just sunny and beautiful, and there's no dehumidification load, you just reject your heat to ambient. Or on 60 degrees and raining, basically was that thought, I would put all of my hot gas to that regeneration coil, because you really don't want cooling, you want dehumidification.
Got it. So you mentioned this is an efficient way to dehumidify the air. You threw out a number there. I think you said 30%.
Yeah.
What is that? Yeah. Less energy usage than conventional, or?
Sure. Yes. So on peak days, you're probably looking at anywhere from 20 to 30% reduction in energy consumption by not overcooling the air and reheating it up, or overcooling mechanically and reheating it back up. Part load operations where it gets really interesting, because we're effectively taking a shortcut on the hardest portion of the psychrometric effort. So for the listeners, every degree colder you push a coil, you're going to pay an exponential penalty on energy, and you're going to get a diminishing return out of it. That's because you're crossing more and more lights of enthalpy as you go down to the left on the psych chart. And we're using the desiccant to do that portion of the not even work, because it's conservational energy process. So as you unload your compressor system into part load operation, more and more of that effort is being, of that net effort is being taken by the desiccant rather than the mechanical refrigeration system. So part load day, we could see anywhere from 30 to 60% energy savings, which is an easy segue into ISMRE if you want to go there, or we could table that for a little bit later.
No, let's do it. I mean, let me ask you this question first.
Sure.
When you're talking to engineers, what's the driving force of trying something new, right? Like I already been doing it with conventional package units for 40 years. I don't want to, 40 years. I don't know how old the guys you're talking to, but you get what I'm saying. For decades, I don't have any problems. I got this new chemistry set you want me to put on the building. What's driving this? Is it energy efficiency typically, Kyle, or?
Yeah. So it's two things. It depends, right? From a pure DOAS perspective, it's an energy driver, Department of Energy, and everybody is laser focused on how do we get more out of how do we get more bang for our buck, right?
Right.
So DOAS side of things, absolutely energy. We're cutting anywhere from 30 to 60% of DOAS energy consumption. Flip side of that, lower dew point, anything depending on vendor, sub 45 degree dew point, you really start, at least historically, have had to start looking at active desiccants, which has a pretty, it's got a cost point associated to it that some people, frankly, don't want to pay for.
Yep, and it gets pricey. Yeah,
it gets pricey. Yeah, saying that nicely, it gets a little expensive.
What's the dew point limit, comfortable limit for your product, for your technology?
about 35. Liquid desiccants can go beyond that,
Right.
but when you get beyond 35 dew point, you get into situations where you might actually need some supplementary regeneration, which with our
Hmm.
system we're not currently doing. So at Mojave, our current product architecture supports down to a 35-degree dew point.
So you fill in that gray
Right.
area niche of DX. DX you're looking at, I say 50 to 45, you're kind of like, that's where you're going to get with DX products typically. Um, but to go to desiccants for 35 is pretty pricey, an active desiccant, but you fill that gap in
Right.
nicely, it sounds like, if desiccant is the driving factor other than,
Right.
efficiency. But
Correct. Yeah. So
nice.
yeah, effectively covering that valley band between 35 and
Hmm.
45-degree dew point, at much closer to conventional commercialized price point, rather than an industrial active
Right.
desiccant price point. So there's that, and then again, just the energy play with even this technology can be applied at 45 to 55-degree dew point, and it's going to cut your energy bill in half. So if that's something that owners or engineers are focused on doing, that's something that this technology can do. It's a different way of skinning the cat for DOAS.
Sure. Sure. I love it. Okay. You mentioned ISMRE.
Yeah.
Did I say that correctly? Did I get all the
Yeah.
initials right? The letters right?
ISMRE.
Why don't you go through that a little bit? That's something actually I need to do some more digging on and do. Maybe you can come back and we can talk about that more in detail. But if you want to introduce that, that'd be
Sure.
great.
So started to float around in 2015. ISMRE, it stands for Integrated Seasonal Moisture Removal Efficiency, and it's a new metric that was introduced by the Department of Energy in roughly 2015, or AHR in 2015, I think, and it's
Hmm.
dictated by AHR 920 instead of 340, 360, which is really for packaged mixed air systems. So AHR 920 is focused on DOAS, or dedicated outside air systems, and it recognizes that DOAS is not really cooling equipment. Ultimately, it's dehumidification equipment.
Mm.
And the Department of Energy and AHR and ASHRAE all assert that the current EER, IER is really not reflective of a DOAS unit's operation from an energy perspective, and not what we should be looking at when we evaluate and compare
Right.
DOAS
Because you
functions.
look at the EER of a DOAS 20-ton unit and it's really low compared to an
Right.
EER of people are like, why are these units so inefficient? And then you got to go through, well, they're not. They're just they're doing a different thing. So I get it. Yeah.
Right. So towards that end, the ASHRAE, HRI all came up with a different way of quantifying it. So ISMRE focuses on not BTUs and how efficiently removing BTUs around like EER does. It focuses on water extraction. So
Mm.
the metric effectively is pounds of water extracted per kilowatt of energy consumed.
Right.
So
Which makes perfect
ISMRE,
sense. Right.
yeah. So there's MRE, which is moisture removal efficiency. You could equate that to like EER. It's a state point. So let's say you have a DOAS unit running 9578, and it spits out a certain MRE. Yeah, so at 9578, bringing it down to, let's say, 55 dew point, because they actually specify dew points and not temperatures. So bringing the air down to a 55 dew point, it's going to extract, I don't know, 5 pounds of water per kilowatt of energy consumed, as an example. ISMRE is the integrated version of that. You can equate it to IER. It's a weighted
Mhm.
average, 4 different points, and it's going to qualify the MRE at those 4 points for any manufacturer. And this is code now at a federal level. So DOAS manufacturers are already doing this and likely publishing them in their submittals. So go look for it. But they take those 4 points, 9578. I'll go to my cheat sheet here. I don't have them all memorized.
No, take your time. While
So
you're
there's
looking
90.
that up. Oh,
Yeah.
go ahead. No, go ahead, please.
So point A, 9578, point B, 8073, point C, 7066, and point D, 6359. Weighted
Are they
averages,
equally
that takes
weighted?
those points. No, actually, they are not. So a lot heavier weighting to the part load points. So
Right. Which makes
9578 is
sense.
only 12%. 8073 is 28, 7066 is 36%, and 6359 is 24%. So very heavily weighted towards that lower average or that lower band of operations, since that's where we see typically most of the dehumidification runtime, or the bulk of the hard dehumidification runtime, I guess I would say.
Sure. And are engineers specifying this value on their drawings currently, or more using it as a guideline?
I think it's probably more of the latter still, though it is quickly, I mean, it's effectively code now. As of May 1st, 2024, all DOAS manufacturers have to provide them. And really, it is the standard that ISMRE is pushing the market to use and move towards for DOAS. Now, just to be clear, it is only for 100% outside air units and 100% outside air units with energy recovery. The moment you have any return air to the unit, technically, you don't have to comply with, there's minimum ISMRE values. You would fall into 340, 360, which is your conventional mixed air systems. But I would say, this is what I tell engineers when I do lunch and learns, anytime you're doing more than 30% outside air, I would say even maybe 20 to 30, you ought to at least look at your ISMRE values on this equipment, because as we know, anything above 20, 25, 30% outside air, you're doing a lot of latent removal, especially in the Southeast, right? Where, things can get real dicey, as I think a lot of people have found real quick if you're doing 40% plus outside air on a mixed air, an engineered mixed air system, if you will.
Yeah, you got to be super careful. That I am currently in North Carolina. That's where I live now. I've been here for about 6 years, but I'm from Florida, and I could tell you, you don't get that outdoor air right.
Yeah,
you could literally be in a school. Like, I've been in so many situations where, we were just starting up the equipment and it wasn't occupied yet, but we were just standing around, and you could tell when the DOAS unit goes off, like someone just flipped the breaker, or they're working on it, and you could literally tell, like, within a minute. That's how bad the humidity is in the air. And I've got this video I show often when I'm doing a psychrometrics prezo of a unit here during the summer, and it's a 50-ton unit, and it's like almost a garden hose just of the condensate coming off of it. It's crazy. And 40% outdoor air is usually harder than handling a DOAS system, because there's misconceptions that, I have an energy recovery wheel, so I'm okay with the humidity in the space. That's a big, that's not true. Anyway, be careful with that. So I'm glad you mentioned that. That's a good point. Okay. So do you have any types of common applications that you see for this product? Like, where do you shine, or is there interesting applications? What do you want to talk about there?
So it's kind of a versatile product, because it can be applied in 2 territories or categories, right? The regular DOAS, which there is some unique stuff I want to talk about that this unit could do from a DOAS perspective. And then also there's the low dew point, more processy stuff. Let's start with the DOAS, because we've been on that thread, and then we'll talk about the low dew point stuff. So from a DOAS perspective, typically we see this paired with your average terminal equipment. So URF systems, frankly, I think liquid desiccant is really the answer for chilled beam, which is a scary product for a lot of people, especially in the Southeast. If you don't handle your dew point, you get rain in your buildings. But
owners are weird about that too. They're not very forgiving on that, as they shouldn't be,
unless it's an architectural feature, right?
Right.
But yeah, so from a DOAS perspective, we've talked about the energy thing, so I'm going to leave that alone. Where we've seen this applied for commercial buildings and in a DOAS application is really around that sweet spot of between 45 and 50 dew point. There's a lot of evidence out there now that suggests that if you're delivering air that a 55, like arbitrarily speccing a 55-degree dew point off your DOAS, you're actually more often than not adding humidity to the space. So it sounds kind of counterintuitive, but a 55 dew point in part load operation, chances are your space is under that. So if you're doing 55 dew point with your outside air DOAS, you're now introducing latent load or humidity into the space that now has to be overcome with a terminal system, like a VRF system or a chill beam or whatever, split system,
Right.
etc. Right. So the idea here is if you utilize something like a liquid desiccant system or just a DOAS in general with a lower dew point, you actually can deliver air that's drier than the space and handle not only the outside air of latent load, but the internal latent load at the DOAS for the space. And that dry outside air will actually absorb the internal latent load of the space. And now your terminal equipment can run drier or effectively dry entirely. So, moisture is an insulator. If we're condensing water on a coil, effectively, you're getting lower efficiency in terms of heat transfer, right? So what we've seen applied with this liquid desiccant system, especially, but just in general with DOAS, and what we suggest to the market is, hey, use this liquid desiccant system, shift load from your terminal system, your latent load specifically from your terminal system to a DOAS, and then you're also shedding some of that load entirely and putting it on this liquid desiccant system that effectively doesn't consume energy, or consumes minor energy in terms of pumping watts instead of refrigeration-based kilowatts. So on the DOAS side of things, we generally push for between 45 and 47 degree dew point, which allows you to achieve that design concept of fully decoupling your latent energy or latent work from the building and doing it purely with DOAS, which allows you to downsize a whole bunch of internal stuff. And it actually, we found, winds up being a lower first cost, because from how many DOAS units are on a building versus that terminal system, typically it's 2 DOAS and 100 terminal units as an example. If you downsize each one 10%, because it's not doing latent work anymore, you got cost savings there. It's going to run more efficiently. You get to downsize your piping, which is, if you're doing BRF, as we move to A2Ls here, not to derail this whole thing and go to A2Ls, but running refrigerant that now is A2L classified, if you're able to shed latent load off of a VRF system, you downsize your piping and get more flexibility on where you get to run that piping. And there's all sorts of benefits to doing a lower dew point in a building, including resilience. It's easier to convert from an office to a lab, all sorts of stuff. So
I get it. Yeah.
You could pick apart different things you want to touch on, but I'm just giving a broad stroke here.
No, that's good. That's good. I haven't thought of it from a diversity standpoint of use of space. So you brought up refrigerants, so I got to double click on that for a second. What refrigerant are you using in your units?
So 454B.
Got it.
Fun fact, actually, we help Copeland. We're using Copeland compressors, Copeland inverters specifically. We actually help them test their new 454B.
Nice.
Inverter compressors in our system. We've been doing it for almost 18 months now. So we launched 454B units back in January of 2024.
Good. Gave you a heads up. Gave you a head start on that. So.
Yeah.
Okay. Well, what about applications other than DOAS?
Sure. Yeah. So low dew point, a couple different areas. So we're doing pools. So that's its own fun area. So we're working on we're doing pool applications. So anytime you're doing like a pool pack or stuff like that, you could actually utilize lower dew points. And you have to be careful, because for those of you that don't do pool applications day to day, if you feed air that's too dry into a pool application, you'll actually suck the water out of the pool and raise your water bills substantially. But it turns out when you use a desiccant material to do moisture removal and manage your humidity load in pools, you could actually back off on your CFM requirements pretty substantially. So the reason you typically need so much air on pool applications is you're locked in based off of a coil temperature. And moisture extraction based off coil temperature, you need more air passes over that coil to get the moisture out. Whereas with liquid desiccant, you're not locked into a coil temperature anymore, and we're able to shave airflow, which is also positive, right?
Right.
So pools are one area where we're applying this technology. Compounding pharmacies, we say a lot of compounding pharmacies where they're getting by with maybe a package RTU that's got a hot gas reheat coil on it. But most of them would generally like a little drier than those rooftop units can get. And they're not going to pay for an active desk because it's just a compounding pharmacy. It's not anything
They're small.
really aggressive. They're
They're
small, right?
usually
Yeah,
small spaces,
you're
and they're
like talking
usually
1,000
getting
square
to
feet.
right, and they want it very cold and very dry, which is a challenge too. We see them in the 40 dew point ish.
Right.
Is that kind of what you're seeing too?
Yeah,
Somewhere in
typically
the
between
40s.
40 and 45.
Hmm.
The lowest we've seen for a compounding pharmacy is about a 38 dew point around
Right.
west. So much drier than typically a package rooftop unit can achieve. But most of them just seem to settle and complain, for lack of a better word,
Hmm.
about not getting the humidity they need to manage their process. And we see a lot of swings on downtime and stuff with regular systems. And hey, can you fix this?
Right.
Now, another area that is really interesting is healthcare. So, as we know, a lot of healthcare applications have these big central plants. Many of them don't have glycol, and they're, you know, we've got a bunch of surgeons and surgery centers and nurses and doctors that
Hmm.
effectively want these spaces really cold because they're garbed up and sweating as they're
Right.
doing these life-saving surgeries and whatnot. And the interesting thing about that is I always hear they really want it cold in the space, but as engineers, I think what we need to interpret from that is they actually don't want it cold. They actually want it dry because
Right.
people are effectively big evaporative coolers. That's how we
Very low
keep
dew
cold.
point.
Yeah, exactly. So if you feed dry air into a surgical suite, they'll actually feel colder, even though it may
Hmm.
not. You don't actually need to drop your temperature down to 45 degrees for them to feel comfortable. If you feed air that's around a 40 dew point, or for surgery centers, typically you see it between 35 and 40 dew point, it'll actually be dry enough that it'll pull water out of people, and you get this evaporative cooling effect. And even though you're garbed up and it's 60 degrees and the space is actually what we recommend, so about 60 dry bulb, 35 to 40 dew point, it'll actually feel more comfortable than maybe 45, 50 degrees, 55 degrees in the space, because you're evaporating that water, wicking that moisture off your skin. So we've done some stuff in that regard to feed surgical spaces and eliminate the need for stuff like pony chillers and glycol systems. And the more interesting part of that, if you want to tie it back to the energy piece, a lot of them have, or well, medical and healthcare has regulations around ASHRAE 170, which is effectively you have to stay under a humidity maximum. And the way they do that currently is typically through electric or hydronic VAV or reheat to keep their space in compliance so they can keep running surgeries. And that's typical where you hear these surgeons getting upset about, hey, it's super hot in here. And the reason that's hot is because they've kicked on their reheat to stay under their 60% maximum to stay compliant. But when you feed dry air into these spaces, that's 35 to 40 dew point, you can actually back off on your electric or zone reheat. And that's where, like, from just a KW spend, you'll, beyond that of a DOAS or a desking application, you'll save a substantial amount of energy just from not using electric reheat to stay under your maximum, because you're so dry that you're not going to get up in the 60% range. So that's kind of long-winded. That's another segment. And then, there's all sorts of different industrial applications that are unique, like washdown situations and stuff like that. But
Sure.
those are probably the more interesting ones that are worth mentioning in our time together today.
No, those are great. Perfect applications. And to the hospital applications, it is a very big challenge if you've got 44-degree water and you're trying to get 40-degree dew point in a space and keep it really cold. You can't really do that. You have to add a pony chiller, like you said, and a whole glycol system, which is a lot harder than it sounds. All the different components that go along with it. And then you got the issue of what are you going to use for reheat if you got a chill water, very cold chill water coil. So anyway, that all sounds great. So efficiency, I like how it fills in the sweet spot of that 35 to 45 and other dew points as well. But that's a Seems like a sweet application for this. And natatoriums, I'll just say too, if you're listening and you don't do a lot of natatoriums, make sure before you do one, you get with someone who knows what they're doing, because they really can be a chat. I mean, all these applications you're talking about, compounding pharmacies, surgical suites, any hospital applications that require low dew point, natatoriums, get with someone who's an expert if you're not regularly designing in those, because it's very unforgiving. If you're off by a few tons or don't have the right feature on a unit, don't have the right to control strategy, you know, guys in there doing surgery, they're not going to stop complaining about it. You're going to have to fix it somehow. And it's usually not, it's very expensive to add a few tons of cooling, if you need to. So anyway, just a word of caution to make sure you get with an expert and get that right the first time. So Kyle, these are made in South Carolina, outside of Greenville, in a city I should know the name of because I'll be down there in a couple of weeks and I can't remember the name of it. So talk a little bit about the manufacturing.
Yeah, so we manufacture these in Anderson, South Carolina.
Okay.
Easy reference point. We're like 10 minutes from Clemson University.
Gotcha.
So, which until I joined Mojave, actually didn't know was in South Carolina. I'm embarrassed to say, but that's okay. So yeah, we make these in South Carolina. Fun fact, we actually comply with Buy America. So for anyone who does government work on the call, I think right now we're floating in about that 70% threshold on source product within our unit from the United States, which we're proud of. Let's see, what else can I tell you about the manufacturing process?
Why don't you talk a little bit about the, we didn't touch on this, but I could imagine people might say, hey, how do we maintain this unit? What is required for maintenance? That might be something that someone might be thinking of the product and be like, well, we don't know how to work on that. So what do you say to that person?
Yeah, no, that's a great question.
This would have fit better earlier in the sequence, but I forgot about it. So
no, that's a good one. So maintenance wise, we actually did. So the bar for us was designing this with the K-12 market involved, which, as you know, K-12 market maintenance, it's got to be very robust.
Right.
Simply. Right.
Right. Because they don't have the big budgets like a lot of these hospitals and everything to have a fully staff. They're doing the best they can. Right.
Exactly. So with that bar in mind, DX system, same as any other DX system, functionally. So hot gas reheat style vapor compression system, nothing really different there. All that standard maintenance is the same. So I'm not going to touch on that. In terms of the liquid desiccant itself, we have spent substantial dollars from an R&D perspective through different grants with NREL, or National Renewable Energy Labs, and Department of Energy to create this system for the liquid desiccant that's very robust. It's functionally, through engineering, a closed loop system. So through engineering closed loop, what does that actually mean? The air does come in direct contact with our liquid desiccant, but we've tested down to parts per trillion with a T, believe it or not. That's doable, to ensure that we're not depleting any of that fluid out of the system and into the air at any point during operational life of the unit. So it's functionally closed loop. We're not depleting any of that fluid. So you never need to top off this desiccant. You never need to replace it, unlike active desiccants, which we didn't get into today. But active desiccants will thermally cycle and start to break down and have to be replaced every 7 to 10 years unless you're really taking care of it. Liquid desiccant is good for the life of the unit. In fact, it's not proprietary. It's just a salt solution. You can actually take it, put it in the next product, the next product, the next product. It'll functionally last forever because it'll thermally cycle infinitely. Because it's a flow rate going through our pads, it's self-washing, self-cleaning. Because it's a brine solution, it's also self-sterilizing. So you do get some natural IAQ benefit out of it. Kind of think like the Dead Sea is a good equivalent. Nothing grows in the Dead Sea because it's too salty. Nothing's completely maintenance free. The only maintenance on this desiccant system itself is we strain the fluid to keep it clean. So any debris that gets past filters, gets past your coils, into the desiccant solution itself is being rinsed out into a buffer tank and being pulled through these mechanical T strainers, where every time you're doing your standard filter maintenance, you usually inspect these things. If there's an ink in it, they just unscrew, you rinse them out with a bottle of water, put them back, and that's really it for the maintenance on that desiccant system. You never need to replace the pads either. They're good for the life because you're just distributing that fluid over it, and we want to keep that fluid clean.
Got it.
That's really that. I get a lot of, is that really it? That's probably a big skepticism item. And then people see
Hmm.
your product in person, they're like, wow, that is really it. Um, so that, yeah,
Okay.
that's it for maintenance on the desiccant system. It's quite robust.
Awesome. Well, I think we did pretty good here today. I think we gave folks an introduction to the liquid desiccants. How do they learn more? You have a YouTube channel we mentioned, Mojave Energy
Sure.
Systems, and your website.
Yeah, so website, Mojave Energy Systems. We have representation across the United States. I would say if you're in the Carolinas, go talk to Air Carolinas because they're our exclusive rep for distribution of our product in the Carolinas. Contact us page on our website. You're more than welcome to reach out to me on LinkedIn. My name's Kyle Troskot. Just send me a direct message. On our website, we've also got a rep locator. Just plug in your zip code and reach out to your local rep. So, or contact us directly on our website, which is mojavehvac.com.
Great. I think that's a good way to end it. Kyle, thank you so much. Maybe you'll come back on in a couple weeks, and I think I'll be down at the factory. We'll do some detailed videos. So if you're listening to this, check out HVAC TV on the YouTube channel and subscribe, and soon you'll see some video of this product as well from the manufacturer. So Kyle, thank you so much.
Yeah, thanks, Tony. Appreciate it. Take care.